Hi, Faye. Hi, Faye. Saki. Hi.
Hi.
30 minutes ago, I was leaving Moffett on Fletcher. I'm sorry, guys. It took me so long. They kept me in there until 10:30. So I apologize about keeping you waiting. But I did make it here, guys. Any questions? Any questions? Faye? Faye? Come online, Faye.
Hi. Sorry,
Hi.
I'm scanning my book.
I have the good news that you gave me a notebook that I wanted. Okay? Finest kind. You got the 9 points for that. All right, Faye?
Yes, thank you.
What that means, Faye, is that just keep it up. Just keep up giving me those same categories because I'm just going to peruse it real quick from now on. Ladies and gentlemen, that's all I want from you from the notebook, okay? I just want you to give me those things I want. Are you able to access my comments?
Yeah.
Saki, Max, are you able to access my comments?
Yeah.
All right. Are you understanding what I'm saying in those comments?
I do understand the comments, but I still struggle with the perfect notes to make.
Look at the exemplar that I gave you, okay?
Yeah.
I got about half the class in here right now. Anybody have anything that they're concerned about in lecture? Anybody have Dr. Selby?
Yeah, I do.
Max, what the hell is he doing?
What do you mean?
Somebody told me yesterday that he's getting into the Bayes equation. Are they correct?
Yeah, they are.
Okay, good enough. All right, you doing okay with it though?
Yeah, I seem to start getting it. We had our first exam yesterday, and I felt like I did pretty good on it.
Finest kind, good. Anybody else have anything that they need to talk about? Lecture or lab? You just want to get this over with so you can go eat lunch. Is that it? All right.
Well, no, but you haven't graded mine yet, so I can't really say anything.
Haven't graded your what?
My notebook.
Okay, did you submit it? I didn't grade the one. Okay, I just got done grading the density notebook. I did not grade the mass percent of a hydrate.
Oh, okay.
I just got that in, okay?
Okay, that's fine. I just wasn't sure which one you were talking about.
Yeah, everybody understand that once you get the notebook so that I'm confident and you know how to do it, then I'm not going to go through and scrutinize it as heavily. But it's in your best interest to keep doing a good job on that because that's the only thing you're allowed to have for the final. Okay? Okay, Max voted that we, sorry, somebody just popped in at the last second. Max voted that we get this started. Ultimately, guys, we're doing the first part of this, the first part of what we're doing today is the same thing we did last week. We're heating up the salt, driving all the water off to get the grams of water that's in there. Same thing, same exact thing. Okay? So are we seeing the PowerPoint that I have up here?
Yeah.
Mm-hmm.
All right, so have you guys have had empirical formulas in intro. Have you had it? How many of you have not had it this semester yet? Max, put your hand up. I know you haven't.
I was just getting ready to say, yeah, we haven't gotten to that yet, surprisingly, but we're in
Anybody?
quantum mechanics.
Has anybody gotten to empirical formulas yet? I haven't gotten to it. Oh, I'm sorry. I'm dealing with intro. This usually, I would have gotten to it by this time. Charlie, have you had this?
I want to say yes.
You've had it before, but you may not realize you've had it.
No, I feel like we're doing this in our lecture right now, or we
Okay.
just did.
I also have empirical formula, but I don't know how good I am at it.
Well, we're going to try and set it down. We're going to set some rules down. And from setting the rules down, hopefully you'll be able to get this. All right. Okay, I need to,
Let's go.
I'm going to go with a couple extra slides here because I want to do something. Okay. Come on, why aren't you doing something for me? Thank you. All right, say I have a compound. Somebody give me a compound. Okay, you won't cooperate.
H2O SO4.
Oh, what am I doing? Come on, stop. H2S, nah, something a little simpler. I'm gonna go with MgCl2, okay? Now, guys, if I have one molecule of MgCl2, how many atoms of magnesium do I have?
1.
Thank you. And chlorine, Charlie?
2.
All right. Trent, 10.
Yes, sir.
You agree with that? If I have one molecule of MgCl2, I have one molecule of Mg, and I have one atom of Mg, 2 atoms of Cl, right?
Yeah, I agree.
All right. What happens if I have 6.02? What happens if I have that many? That should be an E, not a number. What happens if I have that many, 10? If I have that many molecules of MgCl2, how many atoms of Mg do I have?
Do you multiply it by the atomic number that it has?
No. Okay, we just said, 10, if I have one molecule, I have one atom of Mg. Do you agree with that?
Yeah.
If I have 6.02 times 10 to the 23rd molecules of MgCl2, how many atoms of magnesium do I have? What's the
Oh, just
ratio?
one.
Go ahead.
Just one, right?
It's one. Yeah. It's one
No,
to two.
if I have 6.02 times 10 to the 23rd molecules of MgCl2, I have 6.02 e to the 23rd atoms. It's a 1-to-1 relationship, right? One molecule, one atom. So if I have 6.02 times 10 to the 23rd molecules, then I have 6.02 times 10 to the 23rd atoms of magnesium. Are you understanding that?
Yes.
And coincidentally, I have 1.204 e to the 24th atoms of chlorine. Does that make sense? But what is 6.02 times 10 to the 23rd?
Avogadro's number.
And what does Avogadro's number equal? What's that furry little creature that digs under the ground?
1 mole.
So if I have 6.02 times 10 to the 23rd molecules, I have 1 mole of MgCl2, correct?
Yes.
How many moles of Mg? If I have 1 mole of MgCl2, how many moles of Mg do I have? Guys,
One.
we just got
You have one
done
mole.
saying, that 6.02 molecules equals 6.02 e to the 23rd atoms. So 6.02 is equal to 1 mole of atoms. So we have 1 mole of Mg. Moles of Cl,
It's 2.
2, yeah.
all right. Now, do you see this? When we are looking at the subscripts, we are also looking at the molar ratio between the elements in the compound. Does that make sense to you? Does that make
Yes.
sense?
hmm
Subscripts, molar ratio. So if I can determine the molar ratio, I have the subscripts. Does this make sense, guys? I need to have, Carson, I need to have you shake your head yes.
Yes.
Thank you. All right, so we have rules. Empirical formulas are not that difficult if you follow the steps. First step, and this is the hardest one. The first step in any empirical formula problem is the hardest step to do. You got to find the masses of the elements. That's the hardest step to do. Once you do that, second step, turn those masses into moles by multiplying by 1 mole over the atomic weight. Then you're going to look at all those number of moles and you're going to pick the one that is the smallest. You're going to pick the one that's the smallest and you're going to divide it into each of the other moles. When you do that, you've gotten the molar ratio. Now, sometimes when you get a molar ratio, you're going to get a fragment. Has anybody ever seen a chemical formula with a half of an atom, with a third of an atom? Have you ever seen that? So you got to get rid of the fraction. The way you get rid of the fraction is you take that fraction and you multiply it by integers until you get a whole number. If, for example, you have 1.5, you multiply that by 2, you now have 3. If you get 2.33333, if you multiply that by 3, you get 7. But you have to understand when you multiply 1 molar ratio by that integer, you also have to multiply the other one. So if you have a ratio of 2.333 to 1, if you're multiplying the 2.33 by 3 to get 7, you also have to multiply the 1 by 3 to get 3. In other words, 1 to 2.333 is the same as 3 to 7. So what we're doing, we're doing 4 steps to get our final empirical formula. Find the masses. That's going to be the most difficult. Then we're going to turn the masses into moles. Then we're going to divide by the smallest number of moles. That will give us our molar ratio. We have to look at the molar ratio. If there is a fraction somewhere therein, we have to get rid of the fraction by multiplying by a whole number. And then we multiply all the molar ratios by that same whole number. Are we on the same page here? We good?
Yes. hmm
All right, so come on, you can do it. Sorry. Got to find out where I am. I'm way up here. There we go. All right. We have to determine the empirical formula of a iron bromine compound that has a number of waters associated with it. Okay? We need to determine the subscripts X and Y, and we need to determine the coefficient Z. So the first thing, remember what I said, the first step, find the masses. Did we find the mass of water last week?
18.02.
That's the molecular, that's the molecular weight. I'll grant you that. How do we find the waters? Remember last week we had a hydrate. How do we find the water last week?
Mass of the salt minus the hydrate.
Okay, absolutely. What we did was we weighed the stuff to begin with. Then what we did was we heated it. We drove all the water away. Then we took the mass of the hydrate, the compound with water, and we took the mass of the anhydrous without water, subtracted the two, we got the weight of the water. We on the page now? We good with that? So in fact, that's what we're gonna do. I took my crucible and weighed it. It weighed 23.467. I then dumped some of my iron bromide hydrate in there. After I dumped it in, it weighed 25.785. I subtract the two. I get the mass of my hydrate. I then take my crucible, heat it up with a Bunsen burner. All the water goes away. I then take my crucible, cool it, weigh it. I get 25.164 grams. I subtract the weight of the crucible. I now have the weight of my anhydrous. Nothing more than we did last week, right guys? Same thing? Up to this point, we're doing the same thing. We're gonna do something different with the numbers a little later, but to this point, we're doing the same thing. All right. Now, we just heated all the water off, right, ladies and gentlemen? We're gonna do something silly now. We heated all the water away. Now we're gonna add water back. We're gonna add water back so that we get our anhydrous salt back to being the hydrate, but more importantly, it's gonna be dissolved in water. Okay? By the way, we got the mass of the water by taking the hydrate weight, subtracting the anhydrous. That gave us the weight of our water. Now, right now, I have an anhydrous sample, right? What does my anhydrous sample consist of?
Iron and bromine.
Anything else? Is there anything else in there but iron and bromine?
Shouldn't be.
All right. So if we were able to either isolate the iron or the bromine, could we find the weight of the other one?
Yes.
How are we going to do that, Charlie? You just answered
Finding
yes.
the percentage from the molar mass from each.
That's the
Oh,
way
yeah.
you could do it.
Yeah, couldn't you find the molecular weight of both of them and then like find the percent by like dividing by the total molecular weight of the compound?
You can't do that, Max,
No.
because you can't do that because you don't know how many bromines and how many irons there are there. Think
That's
simply.
where I was
Think,
confused.
think more simply. What do you have the weight of? What do we have the weight of?
The anhydrous sample.
So if we isolate either the iron or the bromine,
Subtract that weight from the anhydrous sample.
that's all we're gonna have to do, guys. That's all we're gonna have to do. We're gonna have to do something that will isolate either the iron or the bromine so that we're able to take that stuff, weigh it. That will give the weight of the iron or bromine, then we just have to subtract it from the anhydrous. We have the weight of the other. Okay? We have a very nice thing here. Okay? We have a very nice thing that we can do. We can add aluminum to a solution of FeBr. Anybody remember what kind of reaction this was?
Single displacement.
Single displacement. So what happens in a single displacement? Well, do you remember the Flintstones? Anybody remember the Flintstones?
Yes.
Okay. Fred left Wilma at home. He goes into a bar and sees Barney and Betty. He likes brunettes. Fred takes a shine to Betty. So what Fred does is he's a lot bigger than Barney. So he shoves Barney out of the way and we have a new couple. Fred, Betty, and poor Barney is left on the side of the road. Now, Saki,
Yeah.
have you ever dumped somebody?
What?
Have you ever dumped a guy?
Yeah.
All right, left him for roadkill, right? You left him
Yeah.
on the side of the road. You took the bus and you ran over him 3 or 4 times, right? This poor guy sobbing his eyes out because you saw somebody that looked better, right, Saki?
Okay. Yeah.
Same difference. We're dealing with chemicals. We have bromine. Bromine looks over, sees aluminum, says, aluminum looks much better to me than this iron guy. So what's going to happen is I am going to link with my bromine, and poor little iron is sitting on the side of the road as roadkill. But we've isolated it. When the iron is like this, it's neutral. It's solid iron. So when we add that aluminum to my solution of iron bromine, my iron precipitates out as a solid. So at this point, all I have to do is get a piece of filter paper, weigh it. Then I'm going to do a suction filtration. I'm going to put this filter paper in a funnel and I'm going to pour my solution with solid iron and my, at this point, aluminum bromide solution. The iron's going to collect on the filter paper. I'm going to dry it down. Then once I dry it down, all I have to do is subtract the weight of the filter paper from my iron and filter paper. I have the mass of my iron. We good? Anybody confused about this yet? Okay, hearing crickets, we're going to go on. But as we said, the anhydrous sample is composed of just iron, just bromine. So if I know the weight of my anhydrous sample and I subtract the weight of my iron from it, that gives me the weight of my bromine. So I subtract the iron from the bromine. This gives me 1.376 grams of bromine. Like I said, finding the masses is the hardest part of this. Now I have the mass of water, I have the mass of my iron, and I have the mass of my bromine. I have the masses of everything I need. My next step, find the moles of each. Okay, I'm going to find the moles of my iron by taking my grams of iron and multiplying it by 1 mole over 55.85, which is the atomic weight, I get 0.00575 moles. I take my bromine, my 1.376 grams, multiply that by 1 mole over 79.9, the atomic weight of bromine. This gives me 0.1722, which is smaller, 0.00575 or 0.1722.
0.00575.
So I'm going to divide it into itself. That gives me 1. I'm going to divide it into the moles of bromine. That gives me about 3. This means my molar ratio between iron and bromine is 1:3. Coincidentally, that is those are my subscripts for iron and bromine. Make sense?
Yes.
Got to do one more thing. I got to turn my moles of water into, my grams of water into moles by dividing by 18.02. This gives me 0.0345. I divide 0.0345 by 0.00574. This gives me 5.99, a ratio, 5.99. I've also divided the 0.00574 by 0.00574, so the ratio is 1:6. Overall, the formula is going to be FeBr3.6 H2Os. Questions on that? Questions on what we're doing here, guys? All right. Something that's important. Remember, I said that if we had a fraction, we would multiply it by an integer. Do you remember my saying that?
Yes.
All right. You do that when you're determining the molar ratio of the elements. In other words, when you're determining the subscripts. By definition, when we're dealing with a hydrate, there's 1 mole of the salt, 1 mole of the anhydrous salt for so many moles of the water. So since we can't change the 1 coefficient in front of the salt, we can't multiply by an integer and keep the same molar ratio. So when we're comparing the water to the salt, you round. You don't multiply an integer when you're comparing the moles of water to moles of salt. When you're doing that for the elements, you do multiply by an integer. Give you an example in a second. I have 2.625, another example of what we're doing today. I had 2.625 grams of aluminum sulfide .ZH2O. I heated it and reweighed it to be 1.391. The anhydrous compound was placed in water. I added sodium and I precipitated out 0.500 grams of the aluminum. So I have the weight of the aluminum, that's 0.500. I have the weight of the water because I have the weight of the hydrate minus the anhydrous. So I have the weight of my water. And I have the weight of my sulfur because I have my anhydrous weight. I'm subtracting from that the weight of my aluminum. So I have all 3 weights. 0.500 is the weight of my aluminum. 1.234 is the weight of my water. And 0.891 is the weight of my sulfur. I got all my weights. That's my first step. Second step, convert everything to moles. I divide the 0.5 by 26.98. I get 0.0185 moles of aluminum. I take my 1.234, divide it by 18. I get 0.0684 moles of water. I take my 0.891 divided by 32. I have 0.0278 moles of sulfur. What's the next step I do? Faith, what's the next step that I do?
Divide by the smallest amount of moles.
What is the smallest amount of moles?
The aluminum.
So I'm going to take my sulfur moles divided by aluminum, and I get a 1.50. Moles of aluminum over moles of aluminum is equal to 1. I've got a fraction. Now, when you have a fraction, start with 2. Multiply 2 by the fraction, see if that gives you a whole number. If 2 doesn't work, go to 3. If 3 doesn't work, go to 4. 4 doesn't work, go to 5. When you get to 10, redo the problem because you've probably done something wrong. You're not going to have to multiply the elements by 10. In this case, I have 1.55. If I multiply 1.50 by 2, I get 3. But if I multiply the 1.5 by 2, I have to do the 1 by 2 as well. So that my molar ratio is 1.5 to 1, which is the same as 3 to 2. Okay? So the 2 corresponds with the subscript for my aluminum, the 3 for my subscript for sulfur. All right. Now I'm going to do the same thing. I'm going to take the moles of water and I'm going to divide that by my moles of aluminum. In this case, I get a ratio of 3.6. Remember, right now I'm comparing water to the salt. So when I'm comparing water to the salt, I can't multiply by a whole number because that would change the number in front of the salt. So in this case, I'm just going to take this 3.6 and round it. So that my overall formula is Al2S3 dot 4 H2Os. All right. Going to go through this quick because I've kind of gone through it already. These are the procedures about what is happening when we're dealing with copper chloride .ZH2O. You're going to weigh the crucible, put the hydrate in, weigh it again. Then you're going to heat the crucible, drive all the water off, let the crucible cool. You'll weigh the crucible and the anhydrous again. Okay? The nice thing about this experiment, for you nice to know, is that the anhydrous has a brown color. The hydrate has a blue-green color. So you know immediately whether or not you have done your job in driving the water off. Next, we're going to do a silly thing. We've got our weight of our hydrate and anhydrate. So we're going to do a silly thing now. We're going to take all of our crystals, all of our brown crystals of our anhydrous, we're going to pour them into a beaker and we're going to add water. We're going to quantitatively transfer. Quantitatively transfer means you're going to carefully move it from one vessel to the other. And you're going to add enough water to put in about 15, 20 milliliters of water. You're going to coil an aluminum foil, an aluminum wire. Coil aluminum wire into a coil. Yeah, I'm real verbose right now. And you're going to put it into the solution. Again, we're fortunate with this reaction. Has anybody ever seen HCl before? Or better yet, something I know everybody's seen. Has anybody ever taken table salt, NaCl, and put it into water?
Yeah.
Yes.
What color is it?
It's like it's basically translucent with a little bit of like white dust in it looking.
Well, if it's got the white dust in it, it's not all dissolved. It's pretty translucent. It basically has no color. So if I tell you I put copper chloride into water and it turns blue, where's the color coming from? You just got done telling me that sodium chloride is translucent. So is the chloride imparting any color to the sodium chloride solution?
No.
No,
Then
so
would it impart any color to the copper chloride solution?
No.
no,
What's the blue color coming from?
copper.
The copper is lending it a blue color. So if we are doing the reaction of aluminum plus copper chloride, making aluminum chloride plus copper. How are you gonna know when the reaction's done? Remember, we want to get all the copper out of solution because we want to maximize the amount of copper so that we get all the copper that we started with. How are we going to know when this reaction's done, guys? What's the color of the solution?
Blue.
What's making the blue color?
The
The
copper.
copper. So once the
So,
solution. Oh,
so how are we going to know when the reaction's done?
When the copper turns blue.
No, starts out blue. Remember,
When the copper is fully dissolved.
nope, not when it dissolves. I'm not going to buy that answer either. We have put copper chloride in the water. We've made a blue solution. You've said that the blue color comes from the copper. Remember, this is a copper ion. This reaction is taking copper ion and making copper metal out of it. So how are you going to know when the reaction's over?
When liquid change into colorless or something,
I'm sorry, say that again.
when the blue color is gone.
When the blue color's gone. If all the blue color's gone, is there any more copper ion?
no,
So if there's no more copper ion, then you've transferred all the copper ion and made it into copper metal. Simple enough. So we're going to use suction filtration. We're going to weigh a filter paper, put the copper on it, put the copper solution on it, suck it through. We're going to squirt some ethanol. And you guys kind of know this. Has anybody ever put rubbing alcohol on your hands when you're, for whatever reason? Anybody ever put rubbing alcohol on your skin?
I think I have. I'm not sure.
What did it feel like?
Felt, I guess, kind of hot. Like, I feel like it was burning. I don't know.
Unless you put it in a cut, no. What happens when you put rubbing alcohol on your skin?
Does it feel cold?
It feels cooler because the rubbing alcohol is evaporating. The energy that's causing the rubbing alcohol to evaporate gets removed from your skin. That's why your skin feels cooler. But what also happens? If you've ever done this, your skin looks very, very dry. The rubbing alcohol, as it's evaporating, carries some water with it. So literally, if you spray some alcohol on your copper, as the alcohol evaporates, it's going to carry water away with it. So you've got your copper solid and filter paper. You got the weight of the filter paper, subtract the two, you have your sample. And that is this whole thing in a nutshell. I do offer extra credit on this. During these whole things, during the whole calculations, we made an assumption. What is the assumption we made? You do that, I'll give you 10% of the results section as extra credit. And I don't want to know just that one space at the very beginning that you haven't been doing anything with it. Just type it in there. What assumption are we making in the calculations of this experiment? Now, I've actually done through everything. If you want me to, and my class last night wanted me to, we can go through the reports. Reports are fairly straightforward, just like, wasn't the last experiment easy?
I mean, it's not the experiment itself was difficult, but it was really, really time consuming.
Last week's experiment?
Yeah.
The empirical formula?
No. Mass percent of the hydrate.
Oh, yeah,
That
it's
was-
pretty easy.
Very straightforward.
Yeah.
It was just simple. This one's going to be the same thing. Let's go through it real quick. You can see the screen, right?
Yes.
Okay, so I'm going to go down to this, and we're going to go through the results section. Preview. You can do it. Yes, you can. Start quiz. Okay, mass of the hydrated sample. All you got to do is subtract the weight of the crucible and the hydrate and the crucible. You got it. It's right here. Mass of the dehydrated. You got to show me both of them. Mass of copper. You're going to have a filter paper and a copper plus filter paper. Show me that. Mass of water. Remember, we said you take the mass of the hydrate, subtract the mass of the anhydrous. That will give you the mass of water. Also give me the moles of the water. Up here, you need to give me the moles of the copper. Mass of the chlorine. You have the mass of the anhydrous, subtract the mass of the copper from it. That will give you the mass of the chlorine. Give me the number of moles. Question 5, mole ratio, chlorine, copper in sample. Okay. Basically, what I want you to do, couple things. Dr. Musgrave tricked you. How many of you got the answer to the one question in the pre-lab? You said it was 1 to 2, and you got marked wrong. Did anybody?
Yeah, I did.
Who is I? Carson?
Yeah.
All right. What he did was he worded the question this way. Normally, the way everything is written, cation gets mentioned first, right?
Mhm.
So notice when he asked this question, chlorine to copper. That means you put the copper ratio first and the chlorine second. So instead of being 1 to 2, the correct answer was 2 to 1. Does
Yeah,
that make
I went back and redid it and got it.
Okay,
the
you
other
did
way.
get it right, Carson?
Yeah. For the
Okay.
first time I missed it.
Understand when Dr. Musgrave writes these questions, he does tricky things like this every now and again. So just be aware of it, all right?
No problem.
Now, what I want you to do, I don't care which way you report it out. You do copper to chlorine, chlorine to copper. I don't care. But what I would do for my benefit, if you are reporting copper to chlorine, go 1 to 2 like that, okay? Put what you're putting first, what you're putting second, and then put your molar ratio second. Only what I want you to do is I want you to give me the rough molar estimate. I want the number you get when you divide the smallest number of moles into the largest number of moles. I want that in 3 sig figs, okay? You're going to do the same thing for the water. Again, please put the ratio, how you're reporting the ratio out. And again, I want the rough molar ratio, dividing the number of moles of copper into the moles of water. Again, 3 sig figs. Questions about this? And literally speaking, if you have the answer to the extra credit question, just put it in here. Okay. The post lab is equally simple. Oh, it was right there. The post lab's going to take you through a simulated problem, just like the one we just did in the experiment. You have copper oxygen. You have a sample weighing 0.8232 grams, contains 0.740 grams of copper. Tell me how many moles of copper you have. Second question. Oh, another thing. Do you notice something here, guys? Do you notice what's happening to the numbers? Are you aware of that? When you're dealing with the Dr. Musgrave quiz, be aware that you're not dealing with the same numbers over and over again. He has a formula he uses which switches the numbers around. So each problem is going to be a fresh one. So in this case, you have the anhydrous compound, you have the weight of the copper. Give me the weight of the oxygen. Next question. Again, guys, numbers are different. Numbers are different than the calculations are going to be different. Again, look at this. Right now, you have, this is almost a 2-to-1 ratio, right, guys? Weights? Isn't this almost about a 2-to-1 ratio? 0.9655 to 0.4995?
Yes.
The question down below it, aren't these more 1-to-1?
Yeah.
So you think the empirical formula for the top one is going to be the same as the empirical formula for the bottom one? Just keep that in mind, all right? I guess what I'm trying to say is solve each problem independent. Okay. Fourth step, it gives you new moles, and you're to determine the mole ratio of Y to X. Again, report it out as that, Y to X. Here you have carbon and water, and you're just trying to determine the molar ratio of water to carbon. Again, these 5 questions are doing nothing more than re-emphasizing the points we have already made. I basically have nothing else to say here, guys. Anybody have anything else?
I have a question about the lab when it's asking for the molar ratio or the formula for the dehydrated sample and the hydrated?
Okay, you know, all right, is that Charlie?
Faye.
Faye, I'm sorry, Faye, I didn't
That's
see you. I guess it lights up when I see who's talking, and I should have noticed that. Okay, Faye, you're gonna have to do that for the data table,
hmm
but you don't have to do it in the results section.
well, I don't know how to figure it out for the data. I don't really understand. Is it the same formula? Because
Okay. All right, you understand, Faye, how to get the rough molar ratio?
yes.
Okay. By the way, guys, you're free to go. That's all I had to do. I'm just right now, everybody, if you want to take off, go ahead. If you want to stay and listen, stay and listen.
I'm just
Okay.
confused. In lab, it says that, but that talks about the law of conservation of masses before and after reaction is the same mass. So I assumed it was the same formula.
1 second. All right,
Sorry.
let's go to where you're talking, okay?
Okay.
Are you you're in the lab manual, correct?
I'm looking at my notebook.
All right, are you in the data table, Faye? I'm trying to figure out where you are.
I'm at the data table.
Okay. Good enough. Cool bananas, I can get there. All right. Lab manual. Thank you. All right, I am in here. Where are we at? Are we, maybe not. Maybe not quite yet.
Yeah.
Not quite yet. I'm still in the hydrate. Come on. There we go. Okay, is this what we're talking about?
Yeah, the last two boxes.
All right. Now, I don't know if I can't write it. Okay. You understand how to get this box and this box, right, Faye?
Yeah.
All right. Say you get a mole ratio of 2.5 chlorine to 1 copper.
Okay.
All right. So you're going to have to multiply the 2.5 by 2 to get 5, correct?
Correct.
And you're going to have to multiply the 1 by 2 to get 2, right?
Mm-hmm.
So you have 5 chlorines and 2 coppers. So the formula of the dehydrated sample would be Cu2Cl5.
Okay.
All right. Say you get the molar ratio of water to copper. Say you did that molar ratio and that turned out to be 3.92. I'm sorry, molar, it's water to copper, 3.92 to 1.
Mhm.
Okay. So in the next to last box, you got the subscripts for your salt. So again, you're going to repeat those. Cu2, Cl5 dot. The molar ratio is 3.92 to 1. Remember, I told you when we're dealing with water, you round that one. So that would be dot. It's close to 4 H2O.
So the dehydrated is just the salt.
Correct.
Okay. Okay. Thank you.
Is that what was confusing you, Faye?
Yeah.
Okay.
Yeah. I thought. Never. Yeah. Thank
No
you.
problem. No problem. Anything else, guys?
Thanks, Professor.
No, hey, it's my pleasure. It really is my pleasure. Anybody have anything from lecture you want to talk about? Don't want me to confuse you more, huh? Huh, Max?
I think I'm Professor.
I'm actually good right now.
Good enough. Javier, did you have a question?
No, I was about to head out. Have a good weekend.
You have a good weekend. Take care, guys. Bye.
Take care.
Bye. Hello.
Thank
Goodbye.
you.
Bye-bye. Okay. Stop share. End.